In this lab, we explore diffraction. Diffraction is the phenomenon where when you shine a light through a very tiny opening, you might expect to see a very tiny pattern projected onto a screen. Instead, you see a series of bright and dark bands. The bright bands are due to constructive interference, and the dark bands are due to destructive interference. In part 1 of this lab, we experiment with a single slit and a double slit. And in part 2, we use a diffraction grating and a DVD. With the DVD, we try to find the bit spacing and the ring spacing.
The way that we find aperture using Y1 is by using these two relationships here. So first, we take the Y that we find and the L, which is the distance from the laser to the screen, and then we can find the angle. And then we use that angle in here to find the aperture, because we know the wavelength of the laser. We know that we measured from the first dark spot to the next, and that leaves us with A. In this section of the lab, we're exploring the diffraction pattern through a double slit to find D, which is the spacing between the two slits. We can measure L and Y, and we know M and the wavelength of the helium-neon laser. That way we can use the relationships of tan theta equals Y over L and E sine theta equals M lambda to find the angle and then to find D. So since the dots were really close together on the diffraction pattern, we measured from one M equals 3 to the other M equals 3 and divided by 6 to get Y1. After we found D in this first part, we can use it to find the unknown wavelength of the diode laser. So now we know D, L, Y, and we know M, and we can find the angle using tan theta equals Y over L again, and then we can find the wavelength using the other formula.
In the next few sections, we'll be talking about these two equations, but in different contexts. So this section is centered around a diffraction grating with unknown line spacing. The helium neon laser is set up so that it shines through the diffraction grating to create a pattern on the screen. The screen has to be held up pretty close to the laser because the diffraction pattern spreads out at sharper angles than the double slit does, and the dots end up landing off of the screen. The goal for this portion is to find D, which is the line spacing. This is done by measuring Y and L and using that to find the angle, and then we can use M and the wavelength of the laser and plug in the angle to find D. And if we wanted to know N, we would do 1 over D. In the next section of the lab, we examine the reflection grating off of a CD. A reflection grating is analogous to a diffraction grating, except that instead of looking at the pattern of light that is transmitted through the CD, we're looking at the pattern that is created when the laser is reflected off of the tiny ridges on the CD. This is the really cool part. So to get the ring spacing, that's this picture on the right here. The ring spacing is the ridges that spiral around the CD. We use these equations here again. We measure Y and L, making sure that the laser is pointing in this direction. And then that way we can find D. And then it's a similar method for finding the bit spacing, except you have to make sure the laser is pointing this way. So we measure Y and L again and find that angle and then find D. But this time D is the data bit spacing, whereas in this one D was the ring spacing.
Okay, so for the data and calculation section, for the first experiment, the single slit, we measured the width of the really large peak to be 0.019 meters. Dividing that in half gives us a y1 of 0.0095 meters. And we measured our length to be 1.24 meters. So using the tan inverse equation, we can find our theta, which we got to be 0.438 degrees. And then plugging that in in the other equation, where you have a is equal to p lambda over sine theta at that particular p value, we get an aperture of about 8.26 times 10 to the minus 5 meters. For the double slit, we measured y6 to be 0.023 meters, and dividing that by 6 gave us 0.0383 meters for y1. And we did that, or we're able to do that because we can assume that delta y is constant for a double slit. And our L remained the same at 1.24 meters, so we used the tan inverse equation to find theta, which we got 0.177 degrees, and then we were able to plug that in to the d is equal to m lambda over sine theta equation, and we got d is equal to 2.0476 times 10 to the minus 4 meters, and after error propagation, we figured that d is equal to 2.0 times 10 to the minus 4 meters, plus or minus 0.3 times 10 to the minus 4 meters. So for the second procedure, where we're trying to figure out the wavelength of the unknown laser, we measured y4 to be 0.160 meters. So dividing that by 4, we got 0.004 meters, and we kept L the same again at 1.24 meters. So we used the tan inverse equation to get 0.1848 degrees for theta, and then we plug that into the equation that is lambda is equal to d sine theta over m, where m is equal to 1 in this case, and d is the distance that we found in the previous experiment. So we figured lambda to be 661 nanometers after figuring out the math for that. So for the third experiment, we were trying to find the spacing of a diffraction grating, and so we used pretty much the same setup that we did for finding the spacing of the double slit and the single slit, except for we now had to change L to be 0.1 meters because the distance between the bright fringes is just much bigger with the diffraction grating. So we measured y1 to be 0.043 meters, and using the tan inverse equation, we got that to give us an angle of 23.26 degrees. And then plugging that into the d is equal to m lambda over sine theta equation, you get d is equal to 1.602 times 10 to the minus 6 meters. And for the last experiment that we did with the CD, we did the line spacing first. So our measurements, after reading them, we got y1 to be 0.073 meters, and that was for m is equal to 1, of course. And for L, we measured it to be about 0.0123 meters. We then plugged that into the tan inverse equation again. We got a theta of 30.68 degrees. And we could plug that into the d is equal to m lambda over sine theta equation, and we got 1.24 times 10 to the minus 6 meters for line spacing. And for bit spacing, it was the same equations, except for we had to change the distance a little bit. So L we changed to 0.458 meters, and y1 was measured to be 0.01 meters, and we plugged that into the tan inverse equation and got 1.25 degrees, and then plugged that into the d is equal to m lambda over sine theta equation and got 2.899 times 10 to the minus 5 meters.
In the first part of the lab, we were able to model several different slits. The single slit, we found the aperture, and with the double slit and so on, we found the distance. We were able to use this data to calculate an unknown wavelength of a diode laser. In part 2 of this experiment, we determined the line spacing of a diffraction grating, and then with the DVD, we were able to calculate the bit spacing and the ring spacing. In this lab, we were able to use error propagation. What we did was determine the approximate value we were off with each of our measurements and use the following equation.